So today I'm going to be doing my midterm report for my summer RAU internship with A&M. I want to thank A&M for the opportunity to do this, and also Los Alamos National Laboratory for the opportunity to learn. So the title of this research is Understanding the Catalytic Dimethyl Ether Steam Reforming by Density Functional Theory, or DFT. So over the past month, I've been working with my two mentors, Claire and Anjana, to understand the topic of density functional theory. Unfortunately, my license still hasn't been approved, but I'm working on that to get that done very soon so I can do the molecular calculations. But today, I'm going to be discussing the theory behind this research. This research, it heavily involves dimethyl ether and catalysts. So what is dimethyl ether and what are the catalysts? So dimethyl ether and catalysts. Dimethyl, it's a renewable fuel and a great hydrogen carrier in support of a hydrogen economy. So really the point of the experiment is to create a good hydrogen fuel so that in the future we could use this hydrogen fuel on many things, in cars, whatever. So it has a good hydrogen gravimetric capacity of 13 weight to ratio and a volumetric capacity of 87 kilograms H2 per meters cubed, which is very good for any fuel. With interactions of DME with catalysts of these three molecular compounds, they produce H2 and CO2 as the products. These catalysts have been shown to improve hydrogen selectivity and yield from DME steam reforming, which is really the goal, is to create as much hydrogen as possible. So the next step is how do we understand this reaction mechanism of the DME steam reformation of the newly developed core shell catalysts? So we can understand these catalysts actually without even doing them in person. We can use a density functional theory in VASP, which uses this theory in a simulation setting. So what is VASP? So like I said, it uses this functional theory and it's in a completely virtual environment. So there's physical experiments going on at the Los Alamos National Laboratory with Claire Yang doing these experiments. And comparing these VASP calculations with the experimental values, it'll help create the best possible catalyst for this fuel and increase the hydrogen/carbon dioxide yield. Here's a visual representation of the chemical reaction. So what is this theory? So it has to do with quantum mechanics, which I haven't learned much in school yet since I'm just going to be a junior in college. But from what I understand, it uses the Schrodinger equation, which is just sums up all of ions, electrons, in one equation, the many-particle Schrodinger equation, which is extremely difficult to solve. But so with these n particles, with its own mass, charge, and position, it's notoriously difficult to solve. But this is where density functional theory comes in, using approximations. So there are several approximations that are used, including the Born-Oppenheimer approximation, which makes it so that ions are steady state and where they don't really change, they don't move, which makes the equation much simpler than before. But the ions still have charge, which is created by the potential of the electrons within the compound or the atom. So really the point is to get the electron density of this equation. So using this equation, it contains three terms: the kinetic energy, the potential energy, and the interaction energy of the electrons and protons. And it's able to get the electron density with this equation here, the NR with the integral of all the degrees of freedom of three-dimensional. But So now that we know the electron density along with the ground state energy, which is from the Oppenheimer, so and this is a functional, so it's an approximated equation of the electron density. In this, multiplied by the integral, but this is at several states of time, multiple states of time. So we take the derivative of this to equal 0, which is equal to, with some math with the Schrodinger equation, create this equation of the total electron density, which is density functional theory able to do and see what reactions are able to take place within um, within molecular reactions, which is what we're trying to do and create the best hydrogen yield as possible. Here are my sources. Thank you. Thank you for your time.